Hello students, let's start with a simple but fascinating question. Why does a heavy iron nail sink in water while a massive ship made of iron floats? The answer lies in the relation between density of the body and density of the liquid. Imagine a body of volume V and density ρ immersed in a liquid of density ρ sub L. The body's weight pulls it downward with W equals V times ρ times G. At the same time, the liquid pushes it upward with a maximum buoyant force F sub B dash equals V times ρ sub L times G. Whether the body sinks or floats depends entirely on which of these two forces is greater. Now let's take the first case, the body sinks. This happens when the weight is greater than the buoyant force. Mathematically, W is greater than F sub B dash, or V rho G is greater than V rho sub Lg. This condition is the same as saying that the density of the body is greater than the density of the liquid. In that case, the net force acting on the body is downward. It equals V times open bracket rho minus rho sub L close bracket into G. And that is why an iron nail sinks in water, because its density is higher than water's density. Now the second case, the body floats but remains fully submerged. This occurs when the weight exactly equals the buoyant force. That is W equals F sub B dash, or V rho G equals V rho sub Lg. Here, the density of the body is equal to the density of the liquid. The forces cancel out, the net force is zero, and the body neither rises nor sinks. It simply floats inside the liquid without moving up or down. Such a condition is called neutral buoyancy. Now comes the most common case, the body floats partially above the surface. This happens when the weight is less than the buoyant force. That is W less than F sub B dash, or equivalently, density of the body is less than density of the liquid. In this case, only part of the body's volume, say V, goes underwater until equilibrium is reached. The buoyant force is then V rho sub Lg, which balances the weight W. That is why light substances like cork or wood float with a portion of their volume above water. Their densities are less than water's density. Let's prove this with a simple experiment. Take an iron nail and a piece of cork of the same mass. Place the nail in water, it sinks. Why? Because its density is higher than that of water, so the weight exceeds the buoyant force. Now place the cork. This time, it floats. Cork has a larger volume for the same mass, so its density is lower. The upthrust from water easily balances its weight, and the cork stays on the surface. Next experiment, take a few solid bodies whose densities are already known. If density equals that of water, the body floats but stays fully submerged. If density is less than water, it floats partially. And if density is more than water, it sinks. This clearly shows how the relationship between density of a body and density of the liquid decides its fate, floating or sinking. Now let's derive a useful formula, the fraction of the body that remains submerged when it floats. Take a body of volume V and density ρ floating in a liquid of density ρ sub L. At equilibrium, weight equals buoyant force. So V rho G equals V rho sub Lg, where V is the submerged volume. Cancelling G, we get V over V equals ρ over ρ sub L. This means the fraction of body submerged is equal to the ratio of its density to the density of the liquid. For example, wood has a density about 0.6 times that of water, so roughly 60% of its volume stays underwater and 40% above the surface. So, let's wrap this up. If density of the body is greater than density of liquid, it sinks. If equal, it floats fully submerged. If less, it floats partially above the surface. This principle explains everyday phenomena, from a cork bobbing in water to huge ships floating on oceans. So next time you see something floating or sinking, you'll know it's all about density. I hope this session gave you a clear idea of how density decides flotation. See you in the next session with another fascinating concept of physics.